Okay, so here I will tell you about the density map sharpening approach that we have developed that we call VISDEM. In cryo-EM, due to a contrast loss during the imaging and also later on during the image processing, 3D reconstructions usually have a too strong decay of the radial structure factor distribution. So, so this is shown in this picture here, and this is taken from or modified from this publication. So this shows the Grenier plot, which is the logarithm of your radially averaged structure factor, and so the typical decay that you're seeing it looks like this. So this has all the effects of the structure factor distribution. So this is a relatively strong decay typically, and that means if you have a strong decay in the structure factor, means that all your high resolution terms here they will be weighed down, so that the contribution to the density map will be very small. That means your map appears very smooth and blurred and filtered basically to a low resolution. This decay here is modeled typically with just a Gaussian function. Looks like this. So this defines basically the B factor, which determines how quickly this function decays. And one way of repairing this this fast decay is by multiplying your structure factor distribution with such a Gaussian function using a negative B factor, and that process is called map sharpening. And if you do this, then you're basically pulling up high frequency information and putting more weight onto the high frequency terms in your density map. So ideally, you want to have a distribution that looks like this, so where you have very balanced contributions from all the different structure factors. If you use a too strong negative B factor, then you're over sharpening your density map, then your distribution will look like this, and you're pulling up the high frequencies much too strongly, and the result would be that in your density map you will see a lot of high frequency noise, basically, because this high frequency region here contains, of course, mostly noise. So there's somewhere an optimum B factor that you can use for sharpening your map, and this is done basically always. You always have to do this with your cryo-EM reconstructions, otherwise you wouldn't see any of the fine details like side chains or things like that. So this is a standard procedure. It's also used in X-ray crystallography to improve the density maps, electron density maps that you get, especially if you have lower resolution. Then you often have a too strong or very large B factor, and then you can sharpen your map with a negative B factor. Applying a negative B factors, typically you can, just as an example, you can do this with and rely on very easily. So you just can apply a negative B factor and typically combine this with some low pass filter, and the effect is typically quite drastic. So this would be the raw reconstructions that you get out of your reconstruction program, and then if you sharpen, you suddenly see a lot of additional features and side chains and everything. So sharpening is a crucial step in the image processing. And just as a side note, what we also do often is a local normalization. So this is, for example, implemented in EMAN. With this command, you can locally normalize your map, which also sometimes help if your different parts of your density map are not on the same level. So this is also a typical step that we do. So now we come to the VISDEM sharpening approach. We're trying to use more information for the sharpening than just applying this negative B factor, where you basically multiply your structure factor distribution with an inverted Gaussian. So we have actually much more information about the actual structure factor, the true structure factor, because if you have a cryo-EM reconstruction, you already have a density map, and you know roughly how your atoms are distributed in space. And if you look at the structure factor here in this plot, then the low resolution part of your structure factor is basically determined by the overall shape of your protein and solvent contributions. And the higher frequency part here, this part, is not so much dependent anymore on your protein structure. This is very similar in all protein structures. This is mostly determined by the distribution of atoms, by the packing, by the atom density, by how well your atoms are packed. And this is pretty much the same for all the proteins. And this is shown here. So if we plot the cumulative radial distribution function, computed over, here in this case, 140 randomly chosen PDB structures, and you just took 140 PDB structures and calculated the cumulative radial distribution function here, CRDF, plotted this versus the radius, and then what you get is that here this is the mean, and I also plotted the standard deviation, so you don't really see much variance between these different PDB structures. So this is something that all the proteins share, and this is of course small length scales here, and this determines how the structure factor looks like in this region. And we have the rough shape we have already. We don't have typically, of course, we don't have the atomic model already when we are at this stage of the image processing. We just determined our reconstruction, and now we want to sharpen the density map. We don't have an atomic model, but we have the rough shape of your protein that determines the lower part, and we have an idea of the radial distribution function here, so we know how densely atoms are packed. And for the structure factor here, as I just told you, the exact placement of the atoms is not really important for the high frequency range. So what we're doing in VISDEM now is we're estimating the correct structure factor distribution by randomly placing atoms into the density map. So this is basically going one step further than in the Wilson statistics, where you assume just randomly placement of atoms everywhere. Here we use the fact that we have already the density map and place atoms randomly directly into the map already. Yeah, we place them into this into the reconstruction that we have. And since we are looking at proteins, we're placing already the correct ratio of carbon, nitrogen, oxygen, and sulfur atoms. So we have already the right mixture of atoms, and we have a reasonable packing density. So now the first thing that we have to determine is we have to find the density threshold. So we assume that we know the number of atoms. Typically you know the molecular weight of your protein, so you know how many atoms you need to place. What we have to determine is the density threshold, which basically determines the surface of your protein. So what you can do is you can, and this is done within VISDEM. So we determine automatically this density threshold. So we just try different density thresholds and then look at the radial distribution functions and see which one best fits to the one that we observe in known protein structures from the PDB. And the closest you get to that, that's the threshold that you choose. That is most likely the correct surface of your protein. Yeah, that is the one that we choose. And now that is one information, of course, that we now have. There's also another information that our estimate of the distribution gives us, like this distribution of the atoms that we have placed here. This gives us also information in real space, because now we know how the histogram of density values in our density map looks like. Because that's something that's also, if you in your reconstruction, not exactly ideal, but our estimate here, and we call this a bead model because we throw in just beads or pseudo atoms. That gives us also an idea of the density value distribution. So we have an estimate for the structure factor distribution, that's a reciprocal space information, and we have an idea of the density value histogram, that's real space information. And we want to apply basically both of these restraints to our density map, because that's information that we have, but those are not independent, so we cannot directly apply both of these restraints at the same time. So what we do is we iterate. So the VISDEM method looks like this. So we estimate, first of all, the volume by choosing the density threshold that I just explained to you. Then we generate this pseudo-atomic model, or the bead model. And then we apply the radial structure factor from our bead model. And then we apply the density value histogram from our bead model to the density map in real space. And then we do this again, and thereby trying to get both the structure factor distribution and the density value histogram as close as possible to the estimated values. So this is how this looks like if we apply this to a high resolution density map. So in orange is the original map, and here this is the VISDEM sharpened map. And what we're plotting here is the Fourier shell correlation. So that's a comparison between a density map that we calculate from the atomic model. For instance, we have, of course, an atomic structure here, and compare this to our original map. So this is a model map comparison. This is the black line is with the original density map. And if we sharpen our map with the known PDB structure, this gives us this curve here, and of course the map looks much closer to the model because we sharpen with the correct atomic structure. Interestingly, if we sharpen the density map with this estimated bead model, the pseudo atoms, for which we didn't use any of the known structure information, we get pretty much the same curve. So the map that you get from the pseudo-atomic model, sharpened with the pseudo-atomic model, is very similar to the map that you sharpen with the correct structure factor from the atomic model. There's almost no difference. So the pseudo-atomic model that we use for estimating structure factor distribution and density value histogram is already very close to the correct values. And well, obviously the sharpened density map becomes more similar to the map that you calculate from the atomic model, which means you see already more details. We do the same thing here. So this is the same information that I just showed you for the higher resolution case. We applied this also for lower and very low resolution density maps, and then plotted the density correlation with the correct atomic structure. And you see that you always get an improvement over the best B-factor sharpened maps and the original entry in the data bank, and you see hardly any. There's basically no difference between the VISDEM sharpened and sharpened with the correct PDB model. So the VISDEM already estimates the correct structure factor very well. And if you look at some of the details in the maps, so the sharpening, the VISDEM sharpening gives you typically better defined density maps, better connectivity, like here in this loop region, for example. The original map doesn't show. This is actually the B factor sharpened, the best B factor sharpened map. And this is the VISDEM sharpened map, which gives you better connectivity. Also here in this case, here's missing density in the orange B factor sharpened map. This doesn't look very well. So where you cannot really build an atomic model with a sharpened density map here, you can actually trace the backbone much better. VISDEM is published here, and then it's part of the program is part of directs. You can get directs including VISDEM here on the SimTK website. And the usage is very simple. So you just, this is a command line program. So you read your input map, the mass of your protein, the resolution of your density map, and an output file, and that's it. And maybe I should mention that VISDEM can also estimate the number of atoms for you. So sometimes your reconstruction has flexible parts, and then the density is missing. So even though you think you should see 300 residues, I don't know, 50 of them could be missing due to missing density, and you don't really know how much is missing. One way you could work around this is by defining a density threshold, which you think, visually looking at the map, this could be the surface, this is about the boundary of my protein. Then you can set this here, and VISDEM estimates the right amount of atoms for you. Okay, that's all I wanted to tell you about VISDEM.